will be that K, 2.72 times 5,000 psi. So what does that give us? $13,600. Okay, we wound up a little bit further off on that one, right? Not necessarily a huge problem, but it's, you know, two different ways of coming at it, and you know, it could be a couple of errors in there, right? It could be that maybe SolidWorks, maybe we still needed a more fine mesh in SolidWorks. Maybe we didn't have that mesh fine enough where we really figure out what the actual max is. Maybe we didn't do a real good job of reading exactly what that stress value was off of this chart, right? Like maybe I should have not had 2.72, maybe I should have 2.73 or 2.74, right? It's not necessarily easy to read off of this chart exactly what that should be. So my point with this is this. Using these charts gets you to some level of precision. It's not perfect, right? You're not going to be able to go out to 16 digits and get exactly the same result as someone else, right? But it gives you a really good idea as to how much stress, you know, is actually being experienced in the part once you've accounted for these stress concentration factors. All right? Questions yet? Okay. Yeah, go ahead.
How wide are the margins on the exam?
Okay, he wants to know for the exam just how wide are these margins. I'll show you a couple of different things that we could do. What if I had solved this problem and instead of telling you that the radius of that curve right there was 0.12 instead of 0.1? Everything else is the same. I make the radius of curvature for the fillet 0.12 instead of 0.1. Okay, what that would do is it would shift over to where R over D would calculate to now 0.06 instead of 0.05. So then I could read up this line up to where I hit this curve, and holy moly, that gives you a really solid value of 2.6. That's one of the things that we commonly do on exams to make sure, I mean, we don't always do this, but this is something that is commonly done so that people have a little bit more of a good feeling about it when they've done it right. They can be pretty sure that's probably the number we were shooting for K, okay, as long as you did it right. Now, another thing that we can do there is we'll a lot of times give you results that are only a couple of digits of precision, right? We'll say, is it 2,500 psi, or is it 2,700 psi, or is it 2,900 psi, right? We'll make those more broad so that you can feel like, yeah, I think I've maybe got that right.
That's what I was getting at, because this one we were almost 2,000 psi off.
Right. Although we were that much off. He says for this one we were almost 2,000 psi off. That seems like a lot, right? And I would say it does seem kind of like a lot, but it's not 2,000 psi difference between one person reading the chart and another person reading the same chart, right? It's 2,000 psi difference between a totally other method, finite element method, where we're not even sure what sorts of, we're not super sure for that one what sorts of error we might be introducing because of the nature of that method being an approximation anyway, right? So anyway, all that to say, you're going to be closer than that, being that it's two people trying to read the same chart and answer the question on an exam. Yeah?
I have a question about SolidWorks simulation.
Yeah.
How would we apply a load, a directed load on the inside of like a pin hole, as if we were going to do it for like a truss member?
Okay. He says, what if you wanted to apply on a SolidWorks simulation, you wanted to apply a load to the inside of a hole? Okay? If you want to know what probably the most realistic way to do it is, it's to go ahead and also model the pin, okay, and then put the pin in the hole right? And then specify no penetration, right? What that does is SolidWorks will say, all right, SolidWorks will say, I've been instructed to not allow the pin to move through the material that it is now inserted into. So once it detects that there's going to be contact between the pin and the hole, it will say, I'm not going to let it go through the hole, and I'm going to calculate how much force exists on that surface where the two parts contact each other. So that's probably the most realistic way to do it. Short of that, the other thing that you can do is you can apply a fixture to that hole, right? Like instead of applying the fixture over here on the left end, a quick and dirty way to do this would be to apply the fixture just on that hole and then apply a load to that. Now, that's not exactly right because in real life, only half of the hole is going to be interfacing with the pin because the pin is either going to be pushing to one side of the hole or to the other side of the hole. But it's a way that you can at least get somewhat close, maybe. Yeah. All right, so you want to know, could you put the whole thing together and then load it and see what it would do? If you're trying to model a truss in this thing, okay? There's a few reasons why that becomes difficult, okay? So one of them is you end up needing a fairly fine level of detail at the holes in order to actually be able to resolve the kinds of forces and stresses that occur at the hole. And if you use that level of detail across the whole truss, you end up with a lot of elements, like an insane amount of elements. So there are some tricky things you can do to make it have a tighter mesh in the locations where you need a tighter mesh, and to go to a coarser mesh in locations where you don't need the tighter mesh. It's a little bit outside the scope of what I was planning on teaching you today. Okay? So someday maybe you will be able to use this to do an evaluation of a larger structure. That's not necessarily what my goal is for you. This is mostly, I wanted to at least introduce the idea that you can calculate some stresses in SolidWorks. It'll show you about insights that have to do with the stresses that might occur in members that might not have occurred to you unless you had this to show you, right? We might not have known about stress concentrations unless we had done some sort of an experiment with this, and it starts showing us, hey, it concentrated that stress a lot in these particular locations. Maybe we should do something about that. You know what I'm saying? So there's a couple of goals that I had with today, but it's mostly an intro, right? Just there's this tool available. The nice thing about SolidWorks is it's very easy to learn, believe it or not. It's one of the easiest ones of these packages to learn, in my opinion. And so if you want to play with it, I highly encourage you to start messing around and see what you can make it do. The other factor that would happen with one of these wooden trusses that we're building, that this method is not even going to be able to do it without we'd have to actually introduce a whole other sort of set of tools that SolidWorks had if we wanted to be able to do this. But this is not going to evaluate buckling. Right? That's a whole other kind of analysis that it's not doing in this setup. Okay? So it'll find stresses, but it won't evaluate whether or not something is buckling using our technique that we just used right here. Buckling is another module that's in here, but again, it's more effort to learn how to use. Not saying you can't learn it. I'm just saying it's a little more effort to go in there and figure out how to use it. All right, one last comment, and then I'll let you go.